Problem number 12. We aren't told specifically what vector field f is in this problem. We're told about the curl of f has this formula right here. And then there is a unit square in three-dimensional space. It's found by joining the points 0, 0, 1. There's 0, 0, 1, 1, 0, 1. I'll put that right there. 1, 1, 1. I'll put that right there. 1, 1, 0, 1, 1, put that right there. Connecting them up like this. And orienting this curve in a counterclockwise direction. Okay, so the problem asks us to compute the circulation of f along the curve C that we just drew out here. Well, obviously we can't do this in a straightforward manner because we aren't even told what f is, and so here we have to use Stokes' theorem. So to use Stokes' theorem, this will equal the double integral over a region D of the curl of f. So we'll have to evaluate this integral instead. What is D? D is this region right here. It's a square. It's a flat square. We are going to be orienting D with the upwards normal vector here, because that will correspond to a counterclockwise orientation around the boundary here. How do we parameterize D? We can parameterize D, R of x, y, as x, y, and 1. So the defining feature here of D is that z is always 1. Here x and y can be anything between 0 and 1, and a normal vector can be found by r sub x cross r sub y, gives us 0, 0, 1. Okay, so putting these pieces together, we are integrating as x runs from 0 to 1, y runs from 0 to 1, integrating the curl of f, y, z. Oops, I shouldn't be writing z there because this is when we substitute in our parameterization, z is 1. So let's replace z with 1 right there. And x dot product with our normal vector, 0, 0, 1, dy dx. So integral 0 from 1, 0 to 1, 0 plus 0 plus 1 times x. And so here is our final double integral to evaluate. And this gives us 1/2 here. Okay, that's problem number 12. Take a look at problem number 13. So this is going to be a problem where we are given this region W2. It's going to be a cylinder, filled in cylinder in three-dimensional space, this vector field F. And so we are asked for the flux of F through the boundary of this surface. And so the boundary of the region, that surface there. This is a cylinder. We'd have to do 3 separate vector surface integrals on the top, on the bottom, and on the side to do this. We don't want to do this. So instead, we will use the divergence theorem and evaluate a triple integral over the region W2 itself. So here is our calculation. We have to do the divergence. Let's do a little bit of side calculation here. The divergence of f is going to be partial derivative with this respect to x is 0. The partial derivative with this respect to y is 0. And the partial derivative with this respect to z is 2z. So we are going to be integrating 2z here. And we are going to want to be using cylindrical coordinates here. Cylindrical coordinates will be the easiest. Z will run from 1 to 4. X squared plus y squared is at most 9. Theta will run from 0 to 2 pi. R will run from 0 to 3. Don't forget the r. dz, dr, d theta. Okay, and so how do we do this? We're integrating. Let me move that 2 out in front. Integral is from 0 to 2 pi d theta. I'm just going to factor this as the product of three separate one-dimensional integrals. Okay, so when we compute this out, 2 times this will give us 2 pi. Integral of r from 0 to 3 will give us 9/2. Integral of z, dz, from 1 to 4 will give us 15/2. And if we crunch everything out here, we should get 135 pi.